Network environments are highly entropic. No matter how perfectly a system is designed, hardware inevitably degrades, power supplies fail, and physical cables get disconnected. When a physical topology change occurs, the network must autonomously react, route around the damage, and stabilize itself. In spanning tree protocol, this process of automatic stabilization and recovery is called STP convergence. Look at this redundant triangle topology. If the active primary link fails, a physical backup link is waiting, but the switch refuses to activate it immediately. As that internal timer runs, network traffic halts. It takes between 30 and 50 seconds for that gray backup link to turn green and resume routing. Classic STP mandates this 50-second delay as a mathematically rigid architectural safeguard. Convergence is triggered the moment the physical topology changes, whether from a pulled cable, a switch losing power, or new hardware being connected. But switches do not have eyes. They rely entirely on the continuous flow of network data to map their physical environment. This diagram shows how a switch monitors connections. It listens for a continuous flow of BPDUs. If those incoming packets abruptly stop, the port drops into an alert state. The switch waits for 20 seconds of silence, the max age timer, before declaring the neighbor dead and the topology map invalid. The immediate goal of the system is to restore connectivity by finding the next best physical path to the root bridge. Detecting the failure is only the first step. The switch must now calculate a safe route around the dead link without introducing errors that could destroy the network. If a standby path is perfectly functional and physically connected, the logical question is why the switch doesn't simply activate it instantly to minimize downtime. Imagine a hypothetical scenario where a blocked port immediately transitions to an active forwarding state the second a primary link goes down. In a large topology, network updates are asynchronous. Not all switches learn about a failure at the exact same millisecond. This visualization shows the consequence. On the left, instant cutover overlaps topologies, creating a data loop. Packets multiply exponentially, overwhelming hardware and triggering a broadcast storm. But on the right, timer-based STP holds the backup port in check. It blocks data flow, preventing loops. Instant activation threatens the survival of the entire network infrastructure. The system mandates a delay to ensure the old, loop-prone paths are fully cleared. To prevent a broadcast storm, the switch forces the backup port through mandatory intermediate evaluation states before it can pass traffic. This progress bar tracks the state machine. Leaving blocking, the port enters listening. It processes BPDUs to map the network and verify no loops exist, blocking user data for 15 seconds. Then it enters learning, populating its MAC table for another 15 seconds. These intermediate stages force the network to hold its breath. The hardware strictly verifies loop-free operation before a single packet of payload data is allowed to pass. Only after successfully passing the checks in both the listening and learning states does the port enter the forwarding state. The forwarding state is the operational finish line. The port transitions to solid green, and user data finally flows across the backup link. The total downtime is the sum of these parts. The 20-second max age detection period, followed by 15 seconds for listening and 15 seconds for learning. These additive timers mathematically guarantee a total network convergence delay of 30 to 50 seconds. This 50-second window represents a mathematically rigid timeline of system verification, operating exactly as designed. The core philosophy of classic STP is absolute caution. Loop prevention is prioritized above all else, including the speed of recovery. The protocol is built on the ultimate operational truth of network engineering. It is vastly preferable to endure a short outage than to risk a network-destroying loop. However, in modern high-availability networks, powering data centers, financial markets, or hospital infrastructure, a 50-second outage is no longer acceptable. Because of this severe operational time limit, classic STP's rigid safety mechanisms are considered too slow for today's standards. To solve this, engineers developed an evolutionary upgrade, Rapid Spanning Tree Protocol, or RSTP. Looking at these side-by-side timers, RSTP bypasses the rigid 50-second block. By reducing reliance on fixed timers, it cuts convergence to a few seconds while maintaining network safety. Understanding the rigid 50-second delayed of classic STP is the essential foundation required for mastering the high-speed convergence of modern network protocols.